Hello, this is Pat Hindle, editor at Microwave Journal. It is my pleasure to welcome you all to this webinar in our RF and microwave training series. Today's topic is Advanced RF Silicon-on-Insulator Capabilities for 5G Front-End Modules, presented by Chaojung Lee, Principal Member of the Technical Staff at GlobalFoundries. This webinar will last about an hour, with the first 45 minutes or so for the presentation. The rest of the time will be spent answering your questions. You may submit a question at any time during the presentation. Just use the Q&A box in the WebEx panel here. Please address your questions to all panelists, which is the default setting. This webinar will be recorded and available later on in the events section of the Microwave Journal website. According to 5G Americas, deployment of 5G Phase 1 Release 15 will begin in 2020, with Phase 2 Release 16 following in 2021. And it could be a lot faster the way things are moving along. Innovations in 5G front-end modules, including advances in PA, LNA, and switch technologies and design, are critical for the successful 5G hardware rollouts. This webinar explores potential 5G architectures, analyzes possible requirements for 5G front-end modules, and examines strategies and techniques designers can use to improve PA, LNA, and switch performance to meet 5G front-end module specifications using the advanced Silicon-on-Insulator technology 45 RF SOI, which is the 45 nanometer process recently released by GlobalFoundries. At this point, I'd like to introduce our presenter. Chaojung Lee is a principal member of the technical staff in the GlobalFoundries RF design and technology support team. Prior to joining GlobalFoundries, he was a senior engineer at IBM Microelectronics. His design experience includes couplers, low-noise amplifiers, switches, mixers, phase shifters, VCOs, power amplifiers, dividers and detectors, all for the sub-6 gigahertz WLAN cellular wireless communications, as well as the X and K-band satellite and 5G communication systems. Chaojung has more than 20 publications and holds a bachelor's degree from Zhejiang University and a PhD from Clemson University. So at this point, I will turn the session over to Chaojung.
Hi, good morning, good afternoon, good evening. Thank you for all joining this webinar. And the topic today is Advanced RF for Silicon-on-Insulator capability for 5G front-end module. And we will first review the 5G architecture, and then show some of our calculation about the front-end module potential specification. And then we will show the demonstrator. Before that, we will show some quick introduction about the 45 SOI technology we used in the demonstrator design. So for medium wave, there are many applications like wiregate and also low Earth orbit satellite communication, advanced driver or system for the auto radar, the 5G handset, small cells, millimeter wave backhaul, and another potential application should be augmented reality and virtual reality, optical communication, and so on. And for this first area, there are some common block like first phone antenna, and then switch, power amplifier, LNA, and then power combiner, split, and so on. So this one is a typical 5G millimeter phased area beamformer architecture. In this one, mostly including the antenna system, and then front and module, transceiver, baseband. And in this one is a analog beamformer architecture. We only show the analog beamformer here. The digital beamformer should be also doable. 45 FSY focus for the application, for the switch, LNA PA, power combine, split, up and down converter. For the KA band, because of the sizing, antenna maybe is not be able to integrate on chip, but for the 60 GHz and above, and 45 SI can also integrate the antenna on chip. And because of the high resistive substrate in 45 SOI, based on our university collaborate, the EIRP, can get about 4 dB improvement from the antenna. Okay. Then we'll show some front-end module potential specification. So first is a single comparison between single element and the fixed area. So single element, the advantage is pretty simple and relatively wide radiation pattern. The disadvantage is low value of direction, low gain. And for the fixed area, either for linear or planar or circular, they have high gain advantage. The disadvantage is when the element increase, the total area will also increase. Okay, this is one example from UCSD, and it's a 75 to 85 gigahertz fixed area example. Okay. So how many elements do we use? One element or more, or 4 elements, 2 by 2 or 4 by 4 or 8 by 8. So basic equation, the area EIRP is the power output, single element, minus the single path loss plus the antenna gain, and then plus the gain from the element, 20 log times of number of element number. If we assume the power consumption by other circuit except the PA is power PTH, and the PA efficient is beta PA, then the total system power consumption is this equation equal to the power PA and the other system and times the number of element. Okay, if we put this equation into the EIRP, and then we can calculate based on two scenarios. The first one, if we total power consumption is fixed, and then we can calculate what's the maximum EIRP we can achieve. So that's based on the derivation, we can get the maximum EIRP equal to the power efficient times the antenna gain divided the signal loss, and also has a square positive relationship with the total power consumption divided 4 times of the power consumption by other block. This is maximum EIRP is achieved when this element number equal to this one. The total power consumption divided 2 times of the power consumption by other blocks. Okay. For this equation, anyway, we can know that the maximum EIRP has a direct positive relationship with the PA efficient. Okay. Scenario 2. So for the certain communication span, there is always a requirement for the communication distance. In this case, we need to try to minimize the power consumption for a constant EIRP requirement. Same way, we put this equation into the EIRP equation, we can derive the minimum power based on the EIRP requirement. So basically, the minimum power has a positive relationship with the square root of EIRP and the 1 of the square root of the power efficiency of the PA. And then the orbital mass number of element is related with the EIRP, square root of EIRP, and the signal loss, and also reverse relationship with the power antenna gain efficiency, and antenna gain, and the power consumption by other blocks in the system. So basically, in the following slide, we will show some case based on the scenarization 2. We will fix the EIRP requirement and try to see the power efficient requirement, and maybe we find the best number of elements based on different system requirement. Okay, based on different applications too. This is assumption, calculation assumption. The communication distance is 200 meters. The modulation is based on the field bank multi-carrier modulation. The beamformer width is fixed. The signal noise ratio is 50 dB. The receiver noise figure is 6 dB. And the channel bandwidth is 1 gigabit. Consider this complex modulation. We think the PA is back off 10 to 11 dB. So based on this calculation, EIRP consider 45 dBm and 4 quant required radiation power 24 dBm. So if the area is 2 by 2, the power requirement per element is 19.2. If when we increase the area number, the power will reduce per element to 7.1 for 8 by 8 area case. Inversely, if we can improve the PA efficiency and also the output power per element, then we don't need so much element, and we can reduce the size. Basically, based on our evaluation, and we can see that the following example, the 45 SOI can meet this spec requirement. Okay, more than 8 by 8 area, it may be not feasible for the user equipment set because of the size limitation. Okay, in the following section, before the demonstrator and the design stability, I will have a simple introduction about 45 SOI we used in this in the following design demonstrator design. Okay, 45 SOI is a SOI process. The SOI, the phase was built on the top of a silicon isolated by or buried extra layer from the substrate. So there is, based on the thin-film technology, the transistor have low plastic junction capacitor, and which we are using in high FT Fmax. SOI phase is isolated, and so it can be stacked, which can enable the high voltage and high power handling for the switch and the PA design. SOI substrate engineering, we provide additional RF benefit. So the high substrate, high resistivity substrate will improve the Q factor and of the passive device, and also includes the isolation and linearity. For 45 SOI, based on our measurement, device level measurement, so this is based on one geometry. This is P phase, this is M phase. M phase FT is larger than 300 GHz. Fmax is larger than 315 GHz. And this is P phase FT is about 215, even more than some of geometry. It's a bit more than 215. Fmax is higher than 300 GHz. For the PGK, we support IF model. We also support EM, different kinds of EM tools and the reliability calculation tools. So in 45 SOI, we provide high resistivity handling waveform to improve the back-end loss and reduce the harmonics. So this is 2 back-end option example, and this one is targeted for more digital one, and this one is targeted for the IF minimal application. We added 2 single copper and 1 single aluminum layer. So these 2 single layer copper will be very helpful for the high quality inductor, which is very important for the receiver side, for the LNA load trigger. Okay. For the transmitter side, the PA, the balance or transformer is very useful. These 2 layers is very useful for the balance transformer design. Okay. It will improve the PAE and the P side. This is a comparison of 2 different type of waveform. This one is the green one, green core, is based on the low resistivity substrate transmission line measurement, instead of loss measurement. We can see that when improved to the high resistivity substrate, the instead loss improved a lot. So this is very, very important for the minimal transmission line, low loss transmission line is very helpful for that. And for the, we also provide 3 to 4 layer thin metal layer for the digital block routing. In this process, we also provide high Q, high density, and cap capacitor. It's at the same time, if we want to reduce cost, we also provide the economical vertical lateral capacitor. Okay. We also provide high density resistor if the designer try to integrate the intermediate frequency blocks in the design, and then high density resistor is very important for the RF isolation and also important for low harmonics based on our experience. This PGK is also very friendly for the millimeter wave design. We provide PCR in PCR with chamfering. The chamfering is very important in millimeter wave design. For a small inductor used in millimeter wave, we can see that if it's for a 300 picohenry inductor, if we use chamfering in a radical solution, Lambo, we can see that the Q factor can be improved about 10%. This is not necessary for the sub-6 curve, but it's very important for millimeter wave. We provide this one in the PPA. It's very friendly for the millimeter wave design. Okay, now we are showing the demonstrated design based on 45 SOI, switch design, power amplifier design, and low noise amplifier design. So millimeter wave switch design, they have many different topologies. First one topology is called RF electromechanical switch. This one is not compatible with CMOS technology. We will not talk here. PN diode. PN diode does use a lot in the millimeter wave design. In some of GlobalFoundries process, we do provide that, especially in the bulk technology, because of the low loss, high loss of the substrate. So PN diode is a good option, but it consumes high power, DC power. Another solution, potential solution, is a quarter wavelength transmission band switch for 28 GHz or 39 Ka band switch design. This still occupies a larger area, so it's not durable, but it's suitable for the 60 GHz and above switch applications. Another solution is the phase stack solution, and like the first one, the top plot, like this plot figure, this is a short series and short topology. It occupies very small area. Based on our design, the area is only about 30 micron times about 100 micron size. And this one is called tuned shunt topology. We replaced the series shunt with this inductor. The disadvantage of this one is low isolation. Okay. In the next slide, I'll show you why we will not choose the tuned shunt topology, why we choose a series shunt topology. Okay. Based on our evaluation, the publication, the tuned shunt topology, mostly the insert loss is something about 1.6 to 2, even more than 2 at 28 GHz. So the performance is not as good as this one based on our evaluation with necessary improvement. Okay, this is the design optimized strategy, and for the millimeter switch, we choose the serial shunt topology as we design in this evaluation. We don't use the serial shunt inductor matching to avoid the matching network loss in this frequency. We optimize the stack Lambo to trade off isolation versus insert loss. This is a very simple equation to show the relationship between the isolation, input loss, and isolation. So if the isolation is not good, and then the insert loss will be also worse. So normally we think one stack will show lower insert loss. If we do in the design, that's not really true because of the lower worse isolation. So the insert loss will not be good. So when we choose increase to 2 to 3, the isolation will be improved. So the insert loss will also improve. So we can get find a optimized stack Lambo for the application, for the millimeter wave application. 45 SOI phase provide very good RO, and device left on CF is about 90 frames per second. 45 SOI is an advanced technology, so the pitch is tighter between the drain source or gate to the source. So the traditional metal wiring causes additional coupling and then increase CF. Based on this equation, we can see that isolation relationship with the CF. This one, the CF, when the CF increase, isolation will become worse. So we really need to improve the CF and then improve the isolation, therefore improve the insert loss. So this is very important based on my experience. To improve the CF, it's very important to improve the RF switch performance. So this is one example, KU band SPDT design, and this is a 5-stack SPDT, and this is the layout we use to tape the phase layout to reduce the drain to source coupling, and also in this kind of layout, because the thin low level is a thin metal layer, and the top one is single metal, so there's no reliability concern, and also can induce the practical capacitor between the drain and the source wall, and therefore improve the C-off. This is very useful based on our design experience. So this measurement data, we also monitor the phase level on C-off for single phase with weld to the top single metal. We can see that in low frequency, is about 0.4 ohm per millimeter gateways. When we go up to the Ka band, and we increase to about 0.8. This one is a measurement, insulator loss measurement from 1 GHz to 20 GHz. In 10 GHz, the insulator loss is less than 0.5. And in 20 GHz, the insulator loss is less than 0.9 dB. Okay. This is the return loss. This plot is the return loss and the isolation. In all this frequency range, the return loss is in a reasonable range, and also the isolation. Okay. So larger single measurement, thanks to the help from UCSD Professor Gabriel team, and they did the larger single mesh help for us. So this is the P out and P in measurement based on 40 GHz. So the P1 dB compression point is 31.5 dBm with 5 stack. And this is a 1-ton IIP3 measurement. 1-ton IIP3 is 63.8 dBm. This is the harmonic measurement. The red curve is second harmonic. The green curve is third harmonic. So basically, MD2, MD3 is better than 90 dBc, and the Pmax is better than 25 dBm. This device provides a comparable. If you go to check with a commercial gas solution, and it's a compatible solution. It's a compatible performance with the gas. Another design example is Ka band SPDT. So the first plot, this plot is the SPDT insulator loss. This is a 3-stack solution. So we showed the model hardware correlation. We can see that the model can predicate the hardware pretty well. And in all this from 1 GHz to 50 GHz measurement range, we can see that at 28 GHz, the insulator loss is less than 0.8. And if all the Ka band is less than 1 dB. Okay. We also measured the P out versus P in. Due to the power limitation, we also measured at 40 GHz at UCSD, and the 0.1 dB compression point is about 25 dBm. Okay. The harmonic, second harmonic model hardware correlation pretty very good. The blue curve is the second harmonic. The green curve is the third harmonic. The measurement data for the third harmonic, the modeling data is much better, even better than the simulation data. Overall, this PA can provide P1 dB 30 dBm, 0.1 dB 25 dBm, and this is very. And the software breakdown is about 24, 25, so it can meet the requirement of 23 dB requirement for the from the PA output power point of view. So it can meet the requirement. Now we are talking about the PA. The PA is a core block for the front-end model design. And the design target is when we back off 9 dB, the PAE, we hope the PAE can still be better than 15%. So if we operate the PA in class AB tab or class B tab, the PAE should be larger than 40%. And this is the transceiver site I used in this design. This is the bias condition. Each of them, we bias about 1 volt for each of the device. And the total is about 2.9 volts for this 3-stack solution. And we will display in the next slide about the design stability. So PA design and optimization, design stability. So first one, when we know that for the PA design, the lower stack lambo, we can get a higher PAE because of low practical capacity and connection, right? But because of one device and the P set is also limited. So based on the previous calculation, we know that if we want, there is a P set requirement for different element lambo. If we want to get it high, we want to get the high P-set, and then we can reduce the number of elements. So we evaluate different stack number. We found that when the stack number increases to 4, the PAE will drop to below 40%. And then it will not meet the design target requirement. So we choose 3 stagger in this design can maintain the PAE larger than 40%, and then we try to get the optimized P-set. So to improve the PAE, and we sizing the device to let the real part of the optimal load impedance is close to 50 ohm. Then we don't need to do the impedance transform, reduce the output network loss. Because if we do the transform impedance, and they normally will cause about 1 dB passive loss by the impedance transform. So that's one. That means about 20% PAE drop. Then it will be hard to meet the 40% PAE requirement. So in this design, we do a phase sizing to let the real part of the optimal load impedance close to 50 ohm, and the imaginary part can be cancelled by the RF choke. We use the RC network in the gate to tune the phase and also to avoid the breakdown, especially in the top stack device. We use the ARM and CM to improve the PAE, to tune the PAE. Based on our evaluation, that can improve the PAE about 6%. This is the nice graph of the PA design, including the pad, and it's 550 micron times 750 micron, and this is the small signal measurement. The 1 dB bandwidth of small signal is 18 GHz to 29 GHz. So this is a very wide band PA. In the following slide, we'll show you the larger signal measurement. This larger signal measurement was measured by Georgia Tech in Professor Hua's group. And this is the model hardware correlation, P out versus P in. The red curve is the model simulated data, and the blue curve is the measurement data. And this plot is the PAE versus P in. So we can see that the peak PAE is 41%, corresponding to the P-set is a little bit larger than 60 dBm. When we back off to the 1 dB point, the output 1 dB compression is 14 dBm, and the PAE at the 1 dB compression point is 37%. So overall, if we back off, consider the complex modulation, we need to back off 9.6 dB, and then the PAE, back off PAE, it still can be larger than 50%. So this is good for the complex module applications. And also this shows reasonable model to hardware correlation in the larger signal behavior. This PL can meet the 8x8 area power amplifier requirement based on our previous analysis. This one is larger signal measurement, and we show larger signal bandwidth is also similar as the small signal bandwidth. It ranges from 18 to 29 GHz. So this is very good for the low complex and wideband PA application, because high data rate, we can either increase the bandwidth or increase the modular signal complexity. And then if we use one base, we can see that the tuning range is about 46%. Okay, when you consider the back off, the multi-carrier case, they require high PAPR, and then we back up 10 dB, we can still get about 50% PAE. Okay, so it's good. This PAE is good for both scenario, single carrier or multi-carrier with high PAPR module signals. So we also measured the modular signal. We also did the modulation measurement. High data rate measurement is based on 64 quad, one carrier measurement. So we back up about 6 dB from the peak, we back up 6 dB to 10 dBm of the power. And then the PAE, our PAE is 22.4%. And the EVM is about 5% in this case. So if we require more EVM, we can reduce the bandwidth. It can still support 960 megabit per second data rate at average power of 9.5 dBm, and the average PAE is 22.5%. So the EVM improved to 3.3%. Okay, so this case is based on the single carrier modular signal measurement. So if we want to reduce the phased area element and we need more power, one potential solution is a differential PA. So the differential PA can achieve higher output power and maintain a higher PAE. We use, for the differential PA, we use the neutralizer capacitor and to let the two differential topology balanced in the two set. The differential PA design, there is a main issue is the unbalance. If there is unbalance, we can see that one side could be saturation forced, and then the PR and the PAE will be both dropped. So this one is very important, is very useful for the unbalance of the two single paths of this differential topology. And also, this neutralizer capacitor can cancel the gate to the drain, to the drain coupling, so it can improve the gain. It's very helpful for that. So this is when we do this design, we can see that this is one stage. So we use the input balance to transform the input single-ended to the differential one. In the output side, we use the output balance to transform the differential one to the single-ended. Okay, in the PA design, output balance will be very important. The carbon efficient will be very important to the PAE and also PE side, because this is directly loss added to the output of the PA. Transformer design. So high efficient output of transformer is key for the PA and also for the PA PR and also PAE. So we use a dual. In this process, the dual single metal and high resistivity substrate can reduce the loss of the transformer. And in this design, we use the two top single aluminum and one layer of single copper is used as a primary, and another single copper and a major single copper is used as a secondary. So this is simulates the Q fact of the transformer. At 28 gigahertz, the Q fact is about 24. So this is very good. And also for the transformer, there are different types of transformer, and there is a magnetic capacitor. First one is a magnetic capacitor transformer. For this transformer, the main issue is not symmetrical. As I just explained in the previous slide, for this differential topology, symmetrical is very important. So we didn't choose this one. For the second one, the overlapped one, they can have higher coupling, and the self-resonance is low, and the inductance is high. But based on this one, they can predicate very good symmetrical, okay, as this design example. And based on the design experience, at 28 gigahertz, the self-resonance frequency is still fine for the application. So we choose the overlap and topology in the in this PA application, and we can get to see that. In the sixth slide, we'll show the impact to the PA performance. This is the differential PA layout extraction results, and this is the simulation post-layout simulation data. The gain is about 10.5 dB, and the input loss and output loss is in a reasonable range. But based on our simulation, the input balance has about 2% impact to the peak PAE. Because of the loss in the input balance, the output balance has more effect, and we see about 0.5 dB impact loss to the P side and 5% PAE off to the peak PAE. For the PA simulation, final simulation, we can see that the gain is 10.5 dB power gain, we see the PSAT is 23 dBm PSAT, and 44% of the maximum PAE. Okay. If we, in the future case, we will try to improve the use of advanced topology as a harmonic tuning or duality structure to further improve the peak PAE. In a single-ended structure, we use harmonic tuning. We can improve about 5%. In this one, due to time limitation, we haven't gone to do that. We can get about 34%. And based on the information from our university collaborator, we know that under the duality PA, they can get about more than 23 dBm PSAT, and the peak PAE is more than 40%. So basically, if we choose more improvement for the differential PA, we can also get better, we can also meet the PAE requirement, 40% PAE requirement. So based on this design, we can know that this PA can meet the 4x4 phased area, the power requirement, and also the PAE requirement. Overall, if we consider this PA for the 2x2 phased area, then it may be useful for the low complexity modulation, or useful for the single carrier if the backup for 6 dB rather than 10 dB. And then the differential topology can also be used in 2x2. Another side is the receiver side. So the LNA is a very important one for the receiver side. And this is two topology. Common source one for the first stage is the common source one or cascade one. For the common source one, they either can provide low noise, and it is sensitive to the process of variation, especially for the gate to the drain. So it may be impact, because the gain in here, it may be impact to the high frequency, impact input return loss. Okay. The cascade one, because of the cascade one, the middle capacitor in this one is much smaller because the first stage gain is lower, and in this case, it's much more robust for the process variation, and also it can get higher OIP3. So in the following design, we use this cascade structure as the evaluation. For the low noise amplifier, the noise figure is a very important one. It is related with the communication range or reduce the PA output power for a given range. So based on this design, we can know that this is source degeneration inductor based on the 45 as well FTF max and also the design frequency at 28 kHz. This is source degeneration. The inductor is about 100 picohenry. So this one has limited loss contribution to the LNA. For the gate matching inductor, this one, the inductor is about 700 picohenry at 28 kHz. So this one, based on evaluation, is a major noise contribute to the LNA. And we can, based on the, if we compare it with the ideal case, this one contributes about 0.8 dB noise figure. This is a comparison of the LNA between different substrates, and we use the single-stage cascade LNA divided. The transistor, we did the EM simulation about the gate input matching inductor based on low resistivity or high resistivity substrate are compared. So basically, we see that this is a S parameter, this is the gain and the input return loss, output return loss. We can see that the substrate has a very limited impact to the S parameter except the gain, because this one high Q inductor can reduce the loss, so it can pump the gain about 0.3 to 0.4 dB. Therefore, it will translate to the noise figure. We can see that the noise figure, the minimum, either the minimum noise figure or match noise figure, it improved about 0.3 to 0.4 dB. And so this is a very benefit for the high resistivity substrate, can significantly improve the noise figure about the LNA. Based on some new design, we can see that, and this design is old design. The noise figure is less than 2, and based on some new advanced design, we can see that we can further improve the noise figure. Summary. So basically, we review quick review about the physical area architecture and explain the potential specification for the 28 GHz 5G application. And based on different phase element requirement, we calculate the power requirement for the PA. For the PA is a critical one for the physical element, especially the efficient. It's easy to burn a lot of power and translate to heat rather than get the high power efficient. So the high power efficient is very important for the 5G communication. And then we introduced the 45 SOI. This is the SOI technology, and for the physical area front end module application, we use technology because of the low plastic capacitor. We can get pretty high FT, Fmax, FT larger than 300 GHz, Fmax larger than 315 GHz. So it's very good for the millimeter wave application. And also in the SOI, because of the isolation in the box and also device to device, so the phase can be stacked to improve the power handling of either switch or PA. It's especially important for the switch. So the high usage substrate and the single metal is very important for the LNA point of view. It's very important for the noise figure. For the PA point of view, the output balance, and it's very important for the PA to improve the maintain high PAE and also reasonable P saturation power. We also showed the example, the design example and the design strategy for the switch and the PA and the LNA. For the switch, we optimized the Lambo and also we chose the stack solution and also optimize the Lambo and the layout improvement to get the better insulator loss and also reasonable isolation. For the KU band SPDT, it can provide gas compatible performance for the satellite or 5G communication. For the KA band SPDT, the insulator loss in 28 GHz or even KA band go to 40 GHz. Insulator loss is less than 1 dB with larger than 1 watt output compression point, 1 dB compression point. So this is SPDT can handle the power for 5G user and the equipment application. So based on equation, based on our calculation, the P-SAT should be larger than 23 dBm. This is three stack SPDT design. The 0.1 dB compression point is about 25 dBm, and also the software breakdown. So it will have 2 dB margin for this application. KA band PA, we designed 2 types of PA to satisfy different phase element application. Single-ended one, the P-SAT larger than 6 dBm, the PAE is larger than 40%. So it's good for the 8x8, even complex modulation, or 4x8 for low complex or single carrier application. The measurement shows, the modulation measurement shows that it can get very good PAE and also EVM, less than 3 dB EVM. They can support 1 gigabit/second data rate. For the differential PA, the P-SAT can larger than 23 dBm and the PAE larger than 34%. It can meet the 4x4 area requirement for complex modular signal. For 2x2, it can support the single carrier case. For the LNA, we also showed the KA band LNA can less than 10 dB noise figure, and the substrate resistivity shows a major impact to the LNA noise figure. It's about 0.3 to 0.4 dB improvement compared to the low resistivity substrate. Thank you. That's all my presentation. Do you have any questions?
Yes, thank you very much, Xiaojing. Very interesting presentation. I think this is a great enabling technology for 5G for the future. We have a bunch of questions, so we'll start with the first one. How concerned are you with the heating effects in the SOI technology?
Yes, the SOI definitely will isolate. It's not a good thermal it's not good from a conduction point of view. So in this technology, we provide two solutions. And one solution is the flip chip. And then we use the copper panel to get the thermal out from the side. Another solution is in this technology, we provide a bi-tie. The bi-tie, that means it will go through the silicon dioxide layer, isolation layer, so it can conduct the heat to the backside silicon handling wafer. That one has better thermal conductivity than the silicon dioxide. So there is also a publication by UCSB in the JCC about the evaluation with this bi-tie solution. So yes, from this point of view, yes, we do have a solution, to improve, the thermal issue in the PA design. Thermal is very important. It will impact. If we cannot get the thermal out, it will impact the PAE and also impact the device lifetime.
Great. And next question, is there a shallow trench isolation between transistors in this technology?
Yes. That's the advantage, also advantage of SOI. There's shallow trench between device to device. So we can put it can isolate the device. That can be used, so it can be used in the stack solution to improve the power handling in the switch design. Especially important in switch design. We cannot do like the PA. Like PA, we can use a differential structure, to let the voltage handling in one device will be not high enough, will be not too high to break down the device. But for the switch, and there are two solutions. Either you can use the transmission line structure. This one will occupy a larger area in the KA band or KA band application, and it's not cost efficient. So the stack solution in KA band is still a very important one. It can, the stack can improve the breakdown of the device. Power from the can override the breakdown, the power from the PA. So stack solution can be provided in this SOI technology is isolated from the back and also the side from the device side STI. Yeah.
Okay, and next question is, what's the breakdown voltage of the transistors? How much, output voltage swing can you accommodate by stacking?
Yeah, for single device point of view, there are two kinds of breakdown mechanic. One is the gate breakdown, another is the drain to source breakdown. So it depends on the application, either for the switch application or the PA application. For the switch application, the drain to source breakdown is more than 2 volts. So we can do the calculation based on different requirements and also the waveform requirement, waveform. So we have we did provide the hand calculate or the reliability tool. We can do the hand calculation based on the different lifetime requirement. So to calculate lifetime requirement for the PA or switch application. It's a very good question. It's for production design, it's very important.
Okay, and go ahead.
Yeah, for the PA design, more care about the drain to source breakdown. For the switch design, we may the gate breakdown maybe is also a very important one. And that one, the gate breakdown, and we put low. That's why we also put a high density resistor. This high density resistor can be helpful for the switch design isolation. Yeah.
Okay, could you comment on the PA stability in the example you showed? Is it stable over the entire bandwidth?
Yes, we have single-ended two PA design here, and we we don't see for the single ended one. We load the gain, and the gain is about 30 dB. For high stability is a common issue, especially for the high gain mode. So in this one, we don't see the stability issue. For the differential topology, we use the neutralized capacitor to resolve the stability and to improve the stability issue. Right now, during simulation, we also don't see the stability issue.
And next question, are there on-chip capacitors offered in the 45 RF SOI?
Yes. For 45 SOI, we provide two different types of capacitor. The chip solution is the VN cap. Basically, is a single capacitor, metal-to-metal layer, single capacitor. And also, we provide another two kinds of MIM capacitor. One is called high-density MIM cap. Another one is called high-Q MIM cap. The high-Q MIM cap can be used. It has lower density but much higher Q factor, so it can be used in the signal path, in the millimeter wave signal path. And also, low density is also good for the millimeter wave design because the capacitor will be small, so the low capacitor density will show lower process variation, and the high Q can improve the signal path loss. So we provide these two solutions to improve for the millimeter wave design, and the high Q can be used in the single path, and the high density one especially can be used in the analog one or the intermediate frequency blocks. And the VN cap, we can provide this one is a cheap solution, and it can be used to increase the capacitor density, like the decoupling, like this kind of thing, and to improve the capacitor density. So basically, say we have three capacitor options for different applications.
Okay, and on the transistor models, what frequency are they valid to? The transistor model, for the model, we do provide RF model for the phase and MIM cap, VN cap, resistors, inductors. And for this, our general requirement for the phase, we will calculate to 100 gigahertz. For 100 gigahertz, we will show we did the model hardware correlation for the DC and also the S parameter, noise figure, and we also doing the benchmark circuit design and use this circuit to calibrate the model for the LNA application, for the PA application, switch application. And so, yeah, basically, we tune the model for the device level and also the circuit level to make sure the circuit, make sure the device is good enough for different applications. And we also provide, we have for the RF phase, the thermal issue, thermal self-heating is also included in there. This is a very important one. So we also support support this for thermal simulation for the PA. And okay, and can you talk about the PDK release schedule and support?
The PDK, we released the 0.1 version last December, and we keep improving it. And the 0.5 PDK release will be the mid of this year, and this poor process will be qualified in the end of this year. And also this is a process inherent for the digital process. We have the model hardware correlation for the digital application that is based on even 8 years ago. So we have all this DC correlation. For the new RF application, we did the IF modeling again to improve the model hardware correlation, and also we changed. So the new model hardware correlation and the second 0.5 in middle of this year will be the model will be new hardware verified model. The fully qualified will be the end of this year. But you can see that we have already showed different kinds of circuit design and showed the model hardware correlation, and it looks good either from the switch or from the PA point of view for small signal, larger signal. So yeah, it shows reasonable model hardware correlation. So basically saying this PDK is already ready for the design activity.
Great, and that's an important point to make, that it's both analog and digital can be done on the same chip.
Yes.
Okay, how fast are the transistors in the technology for switching PA designs, and is there a figure of merit for that?
For the switch, the common thing of merit is called R on C off, and for the device level, the R on C off is less than 19 femtoseconds. In fact, when we stack the Lambo increase a little bit to 2 or 3, the stack, the R on C off can be further improved. And the performance is even better based on this one stack solution. That's why I have already explained in the switch design. So I just suggest to use the one stack for the switch application. 2 or 3 stack or maybe 4 is a better one. So if the class requires to handle higher power, so then the FTF max will make the R on C off maybe slightly less than 19 femtoseconds. So also for the switch design point of view, the drain to the source coupling is very important for the switch design. So the back-end layout is very important for the switch performance. And also in this PDK, we provide different pitch. We can improve that. We can change the pitch to improve the drain to the source coupling, and then therefore to improve the switch design performance. And that's mostly for the switch application. For the PA and FTF max, it's a very important one for this technology. The R gate is low, and also in the new model, the R gate is already included in the modeling, so we can have very good model hardware correlation. The F max and can be higher than 315 gigahertz. So it's very good for the not only for the KA band, we are also good for the 60 gigahertz, 70 gigahertz design. So basically, say this device, this active device, is very good for the switch and also PA application. We can see that it can meet, based on different topology, it can meet either switch or PA. It can be made for the 8x8 area or 4x4 area, physical area.
And let's try to fit one quick more question in. There's a couple questions about the LNA noise figure and how that depends on substrate resistivity, and what are your range of resistivities that are available. Yeah, we did a lot of substrate engineering. We cannot show the details of the substrate, but we do provide optimized substrate engineering substrate for this KA band application, and then we can get the best noise figure, and we can get a high Q inductor for the to improve the Q fact, and therefore improve the noise figure of the LNA. But we cannot share the detailed number about the substrate resistivity. Yeah. Okay, great. I think we've run out of time here. I'd like to thank Xiaojun for a great presentation and Global Foundries for sponsoring this webinar. Please visit their website at globalfoundries.com for more information. This webinar has been recorded and will be available to view later on in the events section of the Microwave Journal website. We usually post within about a day or two of the conclusion of today's session. All those who registered will get an email with a link to download a copy of today's slides. And we'd like to thank everybody for joining us today.